Welcome to Maths with EJD. In this video, I continue on complex numbers as we look at operations and polar forms. In the last video, we considered the polar forms of complex numbers, right? And we saw how we could convert from rectangular form to polar form. And I told you that polar forms can be really important when you come to some kind of operations. And on this note, if you have not subscribed to this channel, please do that. Hit the notification bell so you can always get alerted when a new video comes. So let's dive into operations on polar forms. So in this video, we'll be considering the introduction to the idea of operations on polar forms, addition and subtraction of polar forms, multiplication and division of polar forms. Then we'll make a conclusion, and then we'll have some practice questions to play with. And that is it. By way of introduction, we are here to perform arithmetic operations of addition, subtraction, multiplication, and division on complex numbers represented in polar form. So easy. And then addition is here. So if you remember in rectangular form, right? If you have, say you have Z1, you have Z1 equals A plus BI, and you had Z2 equals C plus DI, and you have to do Z1 plus Z2, right? You have to add component by component, real to real. You have A plus C, and complex to complex, this is A plus C. Then complex to complex, you have B plus D, then I in common. So this is the real part and this is the complex part. So that kind of idea is what we use in this situation. And you have it that to add two complex numbers in polar form, you have first one, Z1 is R1 cos theta 1 plus I sin theta 1, and Z2 is R2 cos theta 2 plus I sin theta 2. So Z1 plus Z2 is just straight addition. So you add, of course, if you expand this, right? Normally, if you expand this, you have R1 cos theta 1 plus I R1 sin theta 1. Then here you have R2 cos theta 2 plus I R2 sin theta 2. So, I mean, as you already know from the idea of adding in rectangular coordinates in the rectangular form, so you just add real to real and complex to complex, and that's all you have. So in that case, you just have R1 cos theta 1 plus R2 cos theta 2, and then you have R1 sin theta 1 plus R2 sin theta 2. So that's basically how the addition goes for complex numbers. So let's take one example, to see how this looks like. All right. So this is Z1, which is 2ei raised to power pi over 4. That's more like 2ei raised pi is 180 degrees, I believe. So 180 over 4 is 90 over 2, which is 45. So this is like 45 degrees. That's your Z1. And then Z2 is 3ei raised to pi over 6. That's 180 over 6. That's 60 degrees, right? So to add these two together, you have Z1 plus Z2 equals 2ei pi over 4 plus 3ei pi over 3. All right. And then, so if you want to break this up, right, you already know that REI theta is the same thing as R into cos theta plus I sine theta, like that. So that's why 2ei pi over 4 is the same thing as 2. So 2 now is your R, cos pi over 4 plus I sine pi over 4. So the same thing goes for this. R here is 3, so you have 3 cos pi over 3 plus I sine pi over 3. That's basically what is happening there. So you can then maybe open things up, Now, cos pi over 4, pi over 4 is a special angle. Pi over 4 is 45 degrees, and it's a special angle. And normally, the way we deal with that is we consider a special right angle triangle where, this side where we have this angle to be 45 degrees and we have this other angle again to be 45 degrees. That's looking too small. Let me draw a bigger triangle so we can visualize properly. So you have this now, like this. So this angle, that's not looking like a triangle, but I mean, you get the gist. So this is a right angle. So we take this as 45 degrees, and then this is also 45 degrees. I know the sum of angles in a triangle should be 180 degrees. So this is 45 plus 5, 45, 90 plus 90, that's 180. And then we take this as 1 unit, and we take this one as 1 unit also. All right, because this in the rule of triangle is that angles facing side angle the sides facing angles are proportionate to those angles, meaning that the side facing the biggest angle of a triangle is the longest side. So you can see that's why the hypotenuse here is the longest, because it is facing the angle 90 degrees like this. Okay, so it's the longest. And then these other ones, each of this angle, they are 45 degrees each. So the sides facing them should be equal, right? And that is why we would say this one is 1 and this one is also 1. All right. So having taken care of that, we can get from the Pythagoras rule, this is depending on whichever angle you're considering, this is hypotenuse, this is adjacent, or this is adjacent or hypotenuse. If you're considering this angle, right, this is opposite. If you're considering this is opposite. If you're considering this is opposite. So let's assume you're considering this is opposite, this is adjacent, right? So the hypotenuse will be square root of 1 squared plus 1 squared, right? And that is square root of 2. So it means that the hypotenuse here is root 2. So cos of 45 degrees, cos 45 degrees is actually adjacent, that is 1, over hypotenuse, that is root 2. And you can rationalize that. You have 1 over root 2 times root 2 all over root 2. So it's the same thing like rationalizing in when you are dividing complex numbers. So this is now root 2 all over. Root 2 times root 2 is root 4, and root 4 is 2. And that is why you have this 2 now. This angle is root 2 over 2. So that's why you have 2 root 2 over 2 for this. And again here, interestingly, cos 45 is exactly the same thing. That also follows one law of logarithm, one law of trig, that the sine of an angle is equal to the cos of 90 degrees minus that angle. So you see, the cos of 45 degrees should be the same thing as the sine of 90 minus 45. Interestingly, that's also 95. So 45, right? So if you take this, opposite is again 1, the hypotenuse is also root 2. And if you rationalize, you still get root 2 over 2. And that is why you have this. So you have 2 times this 2 here times I root 2 over 2, because sine 45 and cos 45 are exactly the same, and they are both 1 over root 2. So that's what you have there. And then for cos 60, right? Cos 60 is 1 over 2, because 60 is also a special angle. Cos 60 is 1 over 2, just like sine 30. And then sine 60 is root 3 over 2. I could draw the same triangle like this, something similar to this to explain that. But maybe when I make a series on trigonometry, I'm going to explain all of this in detail. Okay? So here, cos pi over 3 is 1 over 2. So 3 times 1 over 2 is 3 over 2. And then this is sine pi over 3, which is root 3 over 2. So I root 3 over 2 times 3, that's 3I root 3 over 2. Okay, so at this point, we can now add, we add component by component, real to real, complex to complex. Don't forget, this is root 2. So real to real now, of course, you see these 2 cancels these 2. What else cancels? This 2 also cancels these 2. So you have root 2 left. So root 2 plus 3 over 2, that's the real part. For the imaginary part, you have I root 2. So you have I outside root 2, and then you have 3 root 3 root 2. And that is all you can do as far as addition is concerned. So it's just adding real to real and complex to complex, basically. So having taken care of that, so you can go ahead to the next, let's see what we have next. That should be subtraction now. So let's talk about subtraction of complex numbers. As you already know, the idea of subtraction is pretty similar to the idea of addition, except that while addition is commutative, that is 2 plus 3 is equal to 3 plus 2, subtraction is not commutative, because 2 minus 3 is never equal to 3 minus 2, because this is minus 1 while this is 1. But here it's 5 equals 5, like that. Okay, so that's the only difference. But then the rule is basically like the same. So let's see. to subtract two complex numbers in polar form, you have Z1 equals R1 into cos theta plus I sine theta 1. Then Z2 is R2 into cos theta 2 plus I sine theta 2. So to subtract that, you just, as usual, you have R1 cos theta 1 minus R2 cos theta 2, just this. And here R1, don't forget the R1 outside. So I R1 sine theta 1 minus I R1 sine theta 2. That's why I is outside. So you have R1 sine theta 1 minus R2 sine theta 2. Just like the addition thing, So let's take an example like before. So same set, same Z1 and Z2 like we had the other time. So now Z1 minus Z2 becomes 2EI pi over 4 minus 3EI pi over 3. And of course, 2EI pi over 4, again, that is REI theta. Again, that is R into, because EI theta itself is cos theta. We can actually prove that, we can actually prove that, so R is cos theta plus I sine theta, like that. So since that is taken care of, we now have, so we can say that 2EI pi over 4, like we did before, is 2 into cos pi over 4 plus I sine pi over 4 minus 3EI pi over 3. That's 3 cos pi over 3 plus I sine pi over 3. And we do exactly what we did before. So cos pi over 2 is root 2 over 2. Cos pi over 4 rather is root 2 over 2. Sine pi over 4 is root 2 over 2. Of course, this 2 outside is what you have here. This 2 outside here is what you have here. So 2i. And then cos pi over 3 is 1 over 2. 1 over 2 multiplied by 3 is 3 over 2. Then you have sine pi over 3, which is root 3 over 2. Of course, multiplied by 3, and then the I here. So you have 3i this. And then you have some things canceling out, like we had in the case of addition 2. So 2 cancels 2. 2 cancels 2. Then we add root 2, the real part, to minus root 3 over 2, the real part, plus root 2 minus 3 root 3 over 2, like that. So the only thing you can do here is maybe say root 2 minus 3 over 2, this over 1. So the LCM is 2. So 1 in 2. So you have 2 root 2 minus 3 all over 2. That's the best you can do with that. Same here, you can do something similar, but then it's okay this way also. All right. So that's for addition and subtraction. Now, things get more interesting when you move to the concepts of multiplication and division. That's where polar form become really helpful. In fact, in this case, the RE raised to power I theta form is way more useful. So you get to write less, because you just apply the law of indices here. So to multiply two complex numbers in polar form, you have Z1, Z2. Again, don't forget that I theta is the same thing as R cos theta. I keep writing this because it's really like the central theme. So R into cos theta plus I sine theta. So in this case now for Z1, so Z1 is R1 EI theta 1 plus R2 EI theta 2, because we know already that this is R1 into cos theta 1 plus I sine theta 1. And then we know this is something close to that, R2 into cos theta 2 plus I sine theta 2. We know that's what that is. But then instead of wasting time with this, because if you have to multiply these two, it is going to take a long way. You have to say R1 cos theta 1 times R2 cos theta 2, and then you can actually do that, and then you get your result. But then that's too much of trouble, right? Too much of trouble. So in that case, what is advisable to do is to just use the idea of indices that you know already, which is very applicable here. So you have so here you have R1 EI theta 1 plus R2 EI theta 2. So according to the law of indices, of course, R1 and R2, they are just normal numbers that you can multiply, but these ones are exponential, right? So if you have EI theta 1 times EI theta 2, then you can just add up the power. So you have EI theta 1 plus I theta 2, and that is EI into theta 1 plus theta 2. Simple law of indices. And then you get what you have here. Okay? So you get R1, R2. Okay, I have E missing there. I should take care of that. So this is R1, R2, EI that. So it should be R1, R2, E raised to power I into theta 1 plus theta 2, like that. And since you have this, since you already know that REI theta can be written as this, then it only makes sense to say R1, R2, I E raised to power I into theta plus theta 2 is the same thing as R1, R2, just like R before, into cos of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And that makes the whole thing very easy. Makes it very easy. So in that case, we can proceed to do some magic, you know, instead of wasting time and trying to multiply cos and sine and doing all of these plenty things. So here you have Z1. You have Z1 is 2EI pi over 4 and Z2 is 3EI pi over 3. So to multiply that is just to say 2EI pi over 4 times 3EI pi over 3. Then you just multiply the 2 and 3 straight. And then you have E, add the powers up. So you have I into pi over 4 plus pi over 3. LCM of 4 and 3 is 12. So you have 12. So 4 in 12 is 3. 3 times pi, 3 pi. 3 in 12, 4. 4 times pi, 4 pi, like that. So you have 2 times 3 now is 6 here. And then you have e raised power 3 pi over 12 plus 4 pi over 12. Adding these two together, you have 6 times ei 7 pi over 12. And at the end of the day, because this is simply 6 ei 7 pi over 12, then you can expand it. So that's now like 6 cos 7 pi over 12 plus I sine 7 pi over 12. And that's how the addition goes. And if you're interested in getting the angle to the last, then you can convert it to degrees, right? So you have, pi is 180 degrees. So 7 times 180, you multiply that, divide by 12, and you get the cosine of that. And, you can get it down to the last if that's what your interest is about. So that leads us to division of complex numbers. So the law of indices also comes in pretty handy here. So we have Z1 over Z2 equals R1 EI theta 1 over R2 EI theta 2, like that. And then we have, so you can divide this number. For the numbers, you can just divide them straight. And then you apply the law of indices to all these exponential parts. So that's like I theta 1 divided by EI theta 2. So for the law of indices, that's simply EI theta 1 minus I theta 2. And that is E raised to power I into theta 1 minus theta 2, like this. And that's why you have this part. And then going from what you've always had, so you can write that as R1 over R2 into cos theta 1 minus theta 2 plus I sin theta 1 minus theta 2, like that. So with this now, you can actually solve problems if you need to divide complex numbers. So here you have this same set of Z1 and Z2, same Z1 and Z2, like that. So we want to find Z1 over Z2 now. So Z1 over Z2 is simply 2 EI pi over 4 over 3 EI pi over 3. And then 2 over 3 can just divide. And then you have E pi over 4 minus pi over 3. So pi over 4 minus pi over 3. LCM we know is 12. 4 in 12 is 3. 3 times pi, 3 pi minus 3 in 4. 3 in 12, 4. 4 times pi, 4 pi. And 3 minus 4 is minus 1 pi over 12. So that's minus pi over 12. So that's what we have here. And that's what leads to what we exactly have in this case. Okay. So that we now have, so you can now break this down. So this is like your R now. So you have 2 over 3 cos minus pi over 12 plus I sine minus pi over 12 also, which you can leave that way, or you can take further by punching calculator to get the exact values. So in conclusion, you will see that operations on complex numbers in polar form involve manipulating magnitudes and adding or subtracting angles. So for normal magnitudes, you can just add those ones up or multiply. You can multiply those ones or subtract or divide them, right? Especially under division and multiplication. Okay, but then for the angles, when you're multiplying, you add angles. When you subtract, when you are dividing, you subtract angles because they are exponential in nature. And the takeaway from here is that polar form simplifies complex arithmetic operations, especially multiplication and division. All right. So that's the takeaway here. And in the future, you're going to see how that is going to help in so many areas. So for your practice, you can check this out. Try your hands, find the sum, difference, product, quotient. Okay, I forgot to put, yeah. Find the sum, difference, product, and quotient of the following pairs. So that's addition, subtraction, multiplication, and division, right? Of the following pairs. Z1, 4e I pi over 6, and Z2, 3e I pi over 3. Z3, 2e I pi over 4, and Z4, 3e I pi over 3. And Z5, with Z6, 2 cos 30 degrees plus I sin 30 degrees, and Z6, 2 cos 180 degrees plus I sin 180 degrees. And that's how it's been here. Remember to subscribe, press the notification bell so you can always get notified when a new video is released. See you in the next one.